lots of dissipation in it, huh?
I mean, yeah.
Yeah, they're all ending up in the center. That's what you're going to explain. So.
Kind of. I won't talk much about dynamics, but if you're interested, I'm happy to discuss it.
I was going to see if... That solves it. It's enough. All right, let's go ahead and get started here. This is the next series of the ITC Colloquium, and I am pleased to introduce Eric Andersson. He is a postdoctoral researcher at the American Museum of Natural History, where he works with Professor Mordecai Mark McLeod's group. Eric earned his PhD from Lund University, and he specializes in developing and running numerical simulations. And today he will be talking about galaxy simulations with individual stars and the formation of the smallest galaxies.
Very happy to be here. I'm very excited. And yeah, as Kaylee said, I'm going to talk about galaxy simulations and different aspects of what we can learn from these simulations. That's basically what I'm showing you in the background here. It's a movie playing one of the simulations that I've run. It's a simulation that covers the entire age of the universe, starting at redshift 100, going all the way down to redshift 0. And in these simulations, we include dark matter, gas, stars, and different models that we use to, for example, treat star formation, stellar feedback, and things like this. So, because I come from the American Museum of Natural History, I thought it would be fitting to start talking about an anecdote with some historical reference. What I'm showing you here is a depiction from Norse mythology. I myself is from Sweden, so it's an ancient symbol from my culture. And this is a fairly common symbol in many different cultures. It's a depiction of an Ouroboros snake, or a snake that is eating its own tail. This particular example is the Midgard serpent that encloses the Yggdrasil tree, or the tree of the world. And this kind of symbol has been used to depict cycles, especially in nature. And we can draw a similar connection to galaxy evolution. Basically, galaxy evolution is also a cyclic process where we have gas in the universe cooling down and being accreted onto dark matter halos. This gas then becomes dense enough for star formation to occur. The stars inject energy, and this energy then leads to gas expulsion, and then you get this cycle again. And here this is depicted in an artist impression from the review by Tomlinson in 2017. Getting this cycle right is crucial for getting the correct mass, size, internal properties, and chemistry right for galaxies. It's very important that we pay attention to all these different aspects of this process. And it's actually a lot more complicated than what this simple picture shows. If I switch that out, a better representation of this is probably something like this, where, for example, we have physics of wind driving, like this gas expulsion process, is a lot more complicated than just saying energy gets injected and gas leaves the galaxy. So there's an intrinsic complexity here and a very broad range of scales that we need to consider. And because of this, the way that we have been attacking this problem for the past, I would say, 20 years by now, is to run simulations of this process and test different models. This has been a very successful endeavor. Our modern simulations are now able to get galaxies that actually looks like galaxies when we compare them. One of the crucial things that we've learned is that feedback in these galaxies is crucial to solve what has been referred to as the overcooling problem, where all the galaxies would just become too massive ellipticals. But if you introduce feedback into these simulations, and with feedback I mean energy being injected to the interstellar medium. In the case of small galaxies, we typically think of stellar feedback. That's what I will focus on today. But for larger galaxies, we also have AGM feedback, or massive black holes that inject energy. And nowadays, most simulations will get global properties like mass and size correct for galaxies, as I mentioned. We're also able to recreate scaling relations fairly accurately. For example, the mass-metallicity relation is typically solved. It's a fairly well-known problem. But there's still several open questions about this process. I will touch on a few of them today. For example, stellar feedback in a multi-phase interstellar medium is something that has seen a lot of progress in recent years. We also have a lot of data being available, especially through surveys. That means that we have highly detailed data for abundances, etc. in galaxies. And it turns out that yields and chemical mixing are still not well understood processes. By the end of my talk, I will also mention the link between observation and models. This is something that I've been working on recently. So, to give you a brief history of what this has looked like, we have seen an effort towards what's called resolved simulations, and I put big quotation marks here because I don't think galaxy simulations will ever be truly resolved, where we look at the individual atoms one by one. But nonetheless, that's the word people like to use. It's basically simulations where you try to get the structure of the interstellar medium correct, because this turns out to be crucial for this feedback process that I mentioned earlier. One effort has been to simulate stratified disks, which basically means that you take a part of a galaxy, in this case the Milky Way, and you take out this box region, and then you have put a lot of computational effort into resolving this region. But there are some innate problems with this process due to the geometry. For example, you cannot treat things like galactic shear, or it's very hard to treat processes like galactic shear in this type of model. We've also seen people pushing zoom-in simulations and simulations of galaxies that are placed in isolation to parsec or tens of parsecs of resolution. And more recently, we also have seen the advent of what's called star-by-star simulations. And these are simulations where individual stars are traced as particles in the simulation. And I'm showing you an example here. This is from one of my simulations. And that means that now, for a galaxy-scale simulation, we now have to think about things like main sequence stars, AGB stars, black holes, and white dwarfs. All right, so I said that this is a problem that has a huge dynamic range. Basically, we have some object, a galaxy, that is evolving in a cosmological environment, cosmological context. And on the other end, we are interested in processes like star formation and the formation of star clusters and how these stars inject energy into their surroundings. Now, star-by-star models is something that I like to call models that bridge these gaps. So it's basically a model that sits in between. So one example is the INFERNO model that I've been working on. Kaylee has another one called EOS. And in these simulations, we have to take some assumptions from these types of models. For example, we need to assume an initial mass function. We cannot do this self-consistently in these models. And it's also, until recently, been very hard to run these simulations in cosmological environments. So it's kind of in between these two. So what kind of model is a star-by-star model? Well, we can start by thinking about a group of stars. In a classical simulation, or galaxy formation simulation, what you do is you basically take this group of stars and you put them into one particle and you treat them as a single-age stellar population. And that means that your IMF becomes a subgrid model in this particle. So all the things that this particle will do has to assume that we have a well-sampled IMF inside of it. With this star-by-star model, we now start to split up this initial mass function. Most of the models use a mass threshold, and stars more massive than this mass threshold gets injected as individual stars. So we get a picture that looks a bit like this. I mentioned, or I showed a movie of the INFERNO model before. This is the model that I've been working on. And in this model, this mass threshold is actually a parameter that you can change. So whether you want high physical detail or interested in processes that cover specific stars, then you can adapt this mass threshold to get that. This model is implemented in the RAMSES hydrodynamics code written by Roman Tessier, and I'm showing you a movie here that he made fairly recently where he's just blasting the RAMSES logo into oblivion. This is an adaptive mesh refinement code that solves the hydrodynamics, and it also includes collisionless n-body dynamics. One of the key features that I implemented in INFERNO is to treat unresolved dynamical processes. So RAMSES is a collisionless code, so we cannot do things like binary stars or close encounters between stars. These are unresolved. So the way that I solved this issue was to introduce natal kicks based on some velocity distribution. For example, here I'm showing you a velocity distribution that was derived by Owen Krupa in 2016 that gives the velocity of stars that are injected from star formation regions. And basically what I do is I sample this distribution and I apply natal kicks to stars. That means that in these simulations we now have things like runaway stars, for example, stars that escape from their birth environment at very high velocities. There's also a whole lot of process that you need to take into account when it comes to stellar evolution. For example, feedback, mass, momentum, and energy injection now depends on what type of star we're thinking about. For the models that I'll present today, these include stellar winds and supernova injection, and I'm also working on implementing radiative transfer. I also have a chemical enrichment model, so we can look at individual elements in these simulations. So to give an example of what we can do with this type of model, this is one of the few of the first simulations that I ran with INFERNO. This is a Milky Way mass galaxy that has a gas fraction around 20%. So you can think of this as a redshift 2 Milky Way progenitor. If you're into the simulation community, these are the Agora initial conditions. And in this simulation, I was able to resolve all stars more massive than 8 solar masses as individual particles. And what I did was to run 2 simulations of the same galaxy, one where I applied this natal kick model that I showed before, and one where I just didn't include this. So we get one galaxy with runaway stars and one without. That's the way to think about it. And what this comes out to is that you roughly have 14% of massive stars being ejected from the birth environments. Yes?
So you may ask a question you prefer.
No, go ahead.
Yeah, this is really wonderful. So I didn't acknowledge that you have this IMF, but what is the initial special distribution of your star-by-star model?
So the mass function I assume for all this is the one from Krupa in
I'm just
2001.
saying special distribution, like what is the profile, like a radial profile or like three-dimensional profile for them?
So when I get the star formation event, I just put all the particles at the same location and then I kick them out. So there's no distribution. And that's actually important for this project, and I'll show you later what happens.
Like, for instance, H3 survey, they had this special distribution of in situ stars, right? So that would be very interesting to know under these circumstances of runaway or without runaway, how far they can go from their initial concentration.
I'll show you what comes out of this model, actually. But first, like the reason why you would be interested in comparing 2 simulations with and without runaway stars is because when we look at the injection of energy into the interstellar medium, this is a process that actually depends somewhat on the local environment where a star injects its energy. This is 2 movies from Olin in 2019, where he tested explosions in different ambient mediums. These have the same average density, but because of the turbulent structure of this ISM, sometimes the supernova explodes in a very dense region, and sometimes it explodes in one of these cavities. And this has quite big effect on how the supernova bubble evolves. So we wanted to scale this up and test what does this do on a galaxy scale. So here I'm showing you the projected densities of these two galaxies. This one is without runaway stars, and this one is with runaway stars. And these are actually two movies. So when I start them, one thing to notice is that in the case with runaway stars, we get these big bubbles that are fairly long-lived, and these are actually quite rare and much more short-lived in the simulation without runaway stars. And I paused this movie here, and now we can zoom into two of these two regions where we have these clouds. And here I'm showing you the distribution of star particles in these two zoomed-in regions. The red points are unresolved particles, so these are the particles below 8 solar masses that are grouped into one particle. And the white points are these individual particles, more massive than 8 solar masses. I'm also only showing you the young particles, so particles that have not exploded as supernova yet. So all the white points here are particles that will soon explode as supernovae. And in this picture, where we only see the red points, the white points are actually also included. There are still individual stars in this model, but because I don't kick them, they will just remain at the same location as their unresolved particle that they're born with. Whereas when I introduce this kick, you get some distribution. And some of these stars actually escape into these bubbles, where they can then deposit their energy. And to quantify a bit what this does to a galaxy, I'm showing you here the mass loading factor as a function of time. You can, if you're not used to thinking of this parameter, I define it here. It's basically a parameter that tells you like the bang for the buck, or how much do we get out of the feedback that we put in as a function of the fuel that we use for this feedback. And one of the things that I found is that when you introduce runaway stars, you get explosions in the inter-arm regions of this galaxy, inside these big cavities. And you also get fewer explosions in the star-forming environments, so in the spiral arms. So the result is that you get an efficient feedback coupling, but you only have a moderate change in the star formation rate. So that really affects this mass loading parameter. And over gig-years of evolution, this can significantly change how your galaxy evolved. And just by introducing these runaway stars, I saw a 10-fold increase in this mass loading. Now, this is a parameter that is fairly sensitive to where you measure it. So I did measure it at several different distances from the galaxy. And it turns out that this 10-fold increase actually occurs at all these distances. So this has quite drastic effects on what happens to the circumgalactic medium. This is showing two movies of the side-on view of this galaxy. In the bottom here is without runaway stars, and above is with runaway stars. So the story is not quite over here. I did a similar test for a less massive galaxy, basically testing a dwarf galaxy. And here, runaway stars actually doesn't seem to do anything. But there are some reasons for why this is the case. First of all, we have a much lower star formation rate in a lower mass galaxy. And these 5 stars that end up in this void, when you reduce the star formation rate by 2 orders of magnitude, this becomes extremely rare in this type of simulation. We also have an interstellar medium, which is much more porous. There's a much more shallow potential well. So your feedback is mostly dominating by clustered feedback. There's also a small detail, and that is that in these simulations I included type 1a supernova, and those were not included in here. And if you do the math, you actually find that the number of isolated runaway stars is comparable in number to type 1a supernova, and you would expect type 1a supernova to also be somewhat isolated. All right, so I started out by showing you these 3 movies, where I said the star-by-star models actually sit in between these cosmological simulation and these star formation simulations. But what I've been working on for the past year or so is to actually push this model into a cosmological context. And I've done this as part of the EDGE collaboration. This is a collaboration between many people. And I'm listing them here, and highlighted in bold are the people who have been specifically involved in this project that I will present next. Basically, what EDGE is trying to do is to kind of attack galaxy formation from the bottom end of the mass function. We're simulating the smallest galaxies. Basically, these are the building blocks for a hierarchical galaxy formation model. So we want to make sure that our model is correct at the low mass end. And then we're kind of stepping up in masses as we go. Another key important feature or important aspect of this project is that it turns out that dwarf galaxies are very sensitive probes of the approximations that we make for the models that we put into the simulation. This is a figure by Matteo Prugamet showing the iron abundance as a function of V-band magnitude. And basically, when we change assumptions for our models, you can go in different directions of this. For example, feedback tend to move you like this. And if you change the IMF or the radiative feedback model, you can basically move around here as well. And this is quite useful because there's large amounts of data available in the literature, and we can compare our models to kind of constrain what the best choices are. So this takes me to this movie that I showed on the first slide. This is what I refer to as the EDGE INFERNO project, where we were running EDGE simulations, so cosmological simulation of dwarf galaxy formation, applying this INFERNO model. So we're now resolving individual stars in this simulation. In fact, all stars more massive than 0.5 solar masses are resolved as individual particles in this simulation, and it runs from redshift 100 down to redshift 0. So this is a huge computational achievement that we've been able to do. So some details on the models. So these are zoom-in simulations of dwarf galaxies. We're able to reach a resolution of roughly 4 parsec at redshift 0. The resolution actually evolves a bit with redshift, so because of the expansion of the universe. So around redshift 6, when most of the star formation happens, this resolution is around 1 parsec. And I said that all stars more massive than 0.5 solar masses are resolved as individual particles. And this 0.5 solar masses is quite important because that means that all the stars that will evolve past the main sequence in a Hubble time will be resolved as an individual particle. And just comparing the same simulation with and without a star by star, we can see that we get quite a big difference in especially the faint parts of this galaxy, so the outer outskirts. One very important aspect of EDGE is that we don't just run one simulation, we run many simulations of very similar galaxies. The way we do this is applying something called genetically modified initial conditions. Basically, we take a reference simulation that I'm showing here in the middle, and then we go into the initial conditions and we tweak the density distribution. So we get, at redshift 0, a halo with the same mass, but it gets there in slightly different ways. So it grows either faster or slower. And what this looks like in a mass growth diagram, so this is showing the virion mass, or the M200, as a function of redshift for these simulations. We basically have a reference simulation here, and then we can tweak the initial conditions so it either grows a bit faster or forms earlier, or it forms a bit later. But the key aspect here is that we still end up with the same mass at redshift 0. So this is quite important for these galaxies because these are what's called reionization relics. Basically what happens is that when you reach redshift 6 to 4, reionization kicks in. And because these have so low mass, you basically quench star formation at this point. All the gas in this galaxy just boils away, and you end up with something that is more or less gas-free for the remainder of the evolution. And all the growth in stellar mass after this point is through dry mergers. So, for example, this galaxy experiences a dry merger later on, so it grows in stellar mass. But this is actually not because of star formation that happens. So we ran a suite of simulations that we've already ran in the EDGE project using a similar feedback model, but without this star by star. And we see fairly similar growth trends. There is some star formation is a bit is regulated a bit more in the simulation without star by star, but it is kind of within the expected uncertainty that we have in these models. But there is something here to kind of poke a bit at, and that is that there is work that have showed that when your star particles is of order 500 solar masses and less, the IMF is actually not well represented as an average, and you actually do need to do this star-by-star sampling. This is not something that I've had time to look into in detail yet, but this is something that I'm keeping in mind.
So I'll ask a question.
Yes.
Do you also consider conversion of stars to, like, white dwarf or black holes or something?
So I do. So the stellar evolution model includes type 2 supernova for massive stars. And we also have winds during the main sequence for these stars. For lower mass stars, 0.5 to 8 solar masses, we do the AGB, and then we go into white dwarf. And I also, all stars that explode as supernova type 2 also gets converted into black holes. So they are traced in the simulation. All right, so what can we do now when we have a cosmological simulation where individual stars are resolved? Well, first of all, this simulation now includes the actual observable. It includes the stars that we observe in real galaxies. So here I'm showing you the surface brightness of these 4 simulations. And below here, I'm showing you HR diagrams that have been derived directly from this simulation. So this is actually something that now exists in the simulation, and this wasn't the case before. And this is fairly important when it comes to these very small galaxies, because they are very, very challenging to observe. To give you an example of that, I'm showing you here a picture of the Reticulum 2 galaxy, and I like to get my students to try to guess where the galaxies sit in this picture. So far, none of them has succeeded. I don't know if you want to try. But the way that you actually have to do this is you do a photometric survey, and you get either the velocities from these stars, and you can kind of cross-match velocities to pick out what is a group of stars that belong together, or you can match HR diagrams or color magnitude diagrams. And if we do that for this particular galaxy and remove all the background, this is actually the galaxy in this picture. It basically covers the whole image, and there's very, very few stars that are actually observable in this system. And this is a very real limitation of the observations. What I'm showing you here is the limiting R-band magnitude, so only stars with an R-band magnitude greater, or brighter, I should say, brighter than this, is observable. And if we take a galaxy that has a V-band magnitude, for example, -6, which is around the ultra-faint limit, these are only observable out to roughly 400 to 500 kiloparsec with state-of-the-art facilities like the dark energy survey. So my question was that if we do this type of analysis where we try to get the galaxy this way in a simulation, what are the properties that we get for this galaxy? So that's basically what I did. I took these galaxies at redshift 0. I applied a magnitude cut, only considering the stars above this magnitude. So that's shown here. This is, again, the HR diagram, and this is the limit that I imposed. This is 23, which is equivalent to dark energy survey. And in these two examples here, in this case, we see 93 stars, and in this case, we see 49 stars at 400 kiloparsec distance. And I marked them in these two pictures by red circles. So to then determine what the properties of these galaxies are as a whole, you have to apply some pretty careful fitting analysis. Basically, what I did was I took these galaxies and I placed them in an environment with the background. So the red points here are stars that belong to the galaxy, and the black points are just background sources. I then took a density distribution, basically considering this to be a probability function of finding a star in a specific location. And then I did the maximum likelihood fitting to basically fit this distribution. And this is the radial profile that you get out of this. And in this way, you can derive basically the number of stars that the galaxy the model expects that are part of the galaxy, and you also get structural parameters like the half-light radius from this. And when you do that, let there be light, I guess. When you do this, you get something like this. So this is the half-light radius as a function of V-band magnitude. The stars here show what I derive from the simulations using the measurements that we typically use, apply in models. And in the crosses here are mock observed galaxies. And one thing that I find is that you systematically underestimate the V-band magnitude with this approach. And the reason for this is that these galaxies have an extended light profile. I think it's very obvious in the reference simulation, where we have this light profile of the galaxy, but it also includes this halo of stars that you get from mergers, etc. And when you assume a light profile like this, for example, this is in this case an exponential profile, it's almost impossible to account for this extended halo. So you systematically underestimate the number of stars that belong in this galaxy. And this is quite different from what you do in simulations, where you typically just derive your half-light radius, and then you compare in spaces like this to see if your model works. So this is something that we have to be a bit careful about. You can play the same kind of game with, for example, abundance. This is showing the mean iron abundance as a function of V-band magnitude. Now this isn't really, the abundance isn't changed drastically, but we still, of course, see this shift in V-band magnitude. And there's another detail here, and that is something referred to as CMD shot noise. Basically, when we derive properties for this galaxy, we take the CMB and we make a cut in the magnitude, and we only select the stars above this magnitude, or brighter than this magnitude. And whatever stars end up on the giant branch at the time of observation has some stochasticity included in it. In our case, it boils down to the IMF sampling. So whatever mass was sampled for the specific star will determine where it sits on the giant branch or in the CMD at redshift 0 when I observe it. So I did a little experiment where I basically perturbed all the masses. I resampled the IMF, but keeping the stellar masses within 0.25 solar masses of their original mass, and re-derived all these parameters. And I did this 100 times. And what I'm showing you in contours here is the 68 and 95 percentiles of the parameters that you derive this way. And this actually introduced quite a lot of scatter, especially when you're only able to observe of order 50 to 100 stars. It's actually comparable to the scatter that you have in the population. So this is another thing that we should take into consideration when we compare simulations and models. All right, with that, I'm at my final slide. I hope I've convinced you that star-by-star models is an important aspect of the next generation of simulations. When and where stars inject feedback is very important. This is something that we should keep in mind. And now with these types of simulations, we can make direct comparisons with the observed stars. And this brings up questions of how should we actually compare models and simulations. Yeah, with that, I thank you for your attention, and I'm happy to take questions.
I'm wondering how you determined the velocity of the stars and if you varied that in your simulation.
For this, the cosmological simulation?
Sorry, the first part of your talk.
So the way I do it is when you get a star formation event, you basically have a parcel of gas that wants to form stars. And at that point, I sample the IMF, and I put particles at the location of this star-forming region. And then I basically take stars that are more massive than 8 solar masses in this case, and I just sample this velocity distribution. So this is a velocity distribution that was derived from separate simulations by Owen Krupa in 2016, where they just run the dynamical evolution of a star cluster, and they measure basically the velocity distribution of stars that escape this cluster. So I just assume this distribution, and I just sample it, and I kick stars with this velocity.
Okay, thanks. I missed this.
Quick follow-up on that. Do you know if the Owen-Krupa distribution here has been like linked or compared to observations, or it's just a simulation?
So it's very hard to do. So of course it's been compared to observations. The way people typically compare runaway stars is by looking at the fraction of runaway stars that you get. But there is so much debate about what the fraction of runaway stars actually is. I've seen values quoted all the way between 0.5% to 30%. So it's a lot of uncertainty here. And there's not been so many simulations like this run. Like that's one of the big caveats of this model, is that this is a cluster which is 10 to the 4 solar masses. And I just naively apply the same distribution to all my star-forming regions. But ideally, you should maybe make this a function of mass of the cluster that you form in, maybe a function of environment, etc. But I'm still limited to the number of simulations or basically what this distribution is what I need to know. We have some work trying to investigate this in a project called TORCH, where we simulate the formation of star clusters. That's basically one example is shown here, where we do a hydrodynamical simulation with the zinc particles prescription for star formation, and then we actually apply proper direct n-body to get the dynamics right in this process. And my hope is that we will be able to measure the velocity distribution from this kind of model, and also the runaway fraction.
Cool. Thank you.
Okay, so you brought up reticulum too, and I'm wondering if you have a way of modeling our process elements, and how do you do that without binaries?
So I tried. I put in a model for europium, and I included a model for neutron star mergers to kind of produce it. But this model is very uncertain, and it turned out that europium is pretty much broken in these simulations. So it's still very hard to do in something that I'm working on.
Okay, awesome.
So the question is about the comparison between simulation and the observation. And you said you set a kind of threshold of magnitude to rule out the star phantoms to sun. But in the real observation, we observe the surface brightness rather than the magnitude of the star. So will this change the comparison, because you probably have very dense stellar field, and the magnitude of individual star will still be faint, but you can still observe this kind of surface brightness. And the second thing is about, you say we lose the luminosity from the halo stars. And is there any uniform correction factors can be used for the observation?
So that's an excellent point. So one of the reasons why you can put a limiting magnitude is because these are very faint systems. So to be able to find them in the first place, you need to apply a lot of clever machinery. The way I kind of investigated here is that to pick out something like the reticulum 2, you actually get a photometric survey. And this one has a point spread magnitude limit, or a magnitude limit on the point spread function, which is why you can do things like why you can make a plot like this, right? Where you get limiting magnitude as a function of distance and galaxy magnitude. But there are a lot more uncertainty here, right? I basically did the best case scenario. Another thing that is like, if you discover a star very, very far away, will you attribute it to this galaxy or not? I would say my estimates are the best case scenario where you observe the stars in this galaxy. You see what I mean? But yeah, we can do a lot more. And also in this example, this is just one case, 400 kiloparsec, and ideally you would like to have this as a function of distance, as a function of total V-band magnitude for different galaxies, and also as a function of whatever background you assume for this particular galaxy.
That was all really interesting. So the comparison that you showed with and without stellar initial kicks of the CGM, I thought was really striking. The first question is, what's actually going on there? What is the mechanism for way more feedback, I guess, with runaways? And then my second question is, what feedback do you have turned on in this scenario? You said at the beginning there's no AGN feedback.
Yeah, so for the simulations, I don't include any AGN. It's an isolated Milky Way-like disk. For the feedback, I include type 2 supernova, winds during the main sequence for very massive stars. These are fast stellar winds, and also AGB winds. But the AGB winds are pretty much negligible for this galaxy. And it's like I've been debating with people about what is actually causing this. It's not super easy to nail down, especially there's a few examples in the literature where they do similar tests with slightly different setups and they don't see this effect. And there are some examples in the literature when you see an even bigger effect. And there's probably an element of like numerical resolution here and numerical modeling. What I think is going on is actually this, that you have basically stars that get into the inter-arm regions of these galaxies. And you basically, this is not just a region where the supernova bubble can expand freely, it's also a chimney that kind of connects you directly into the CGM. So that also increases the amount of mass that you can inject. But there's...
What is that distance?
So this distance is, I think, 8 kiloparsec. So I would say, yeah, this is like, probably here is like 10 kiloparsec.
Great talk. So about the same slide, do you understand the difference between Milky Way and dwarf galaxies? Why you don't see the same thing in the dwarf regime?
So it can be a lot of things. One of the two things I point out here is that basically when I look for isolated runaway stars in these dwarf galaxies, I find maybe one or two over the course of a few million years. So they are very, very rare to get stars that escape this. Like the velocity distribution, I assume, is a pretty steep power law. So getting a star that can fly off to 1 kiloparsec distance, you would need like a few hundred kilometers per second kick. And they basically don't happen in this simulation just because you have too few stars. You also have a much shallower potential well. That means that I think you've basically saturated your wind. You're just not gonna see much change when you change your model. And I think this type 1a comparison, like that shouldn't be underestimated. Like these simulations didn't include type 1a supernova, but these did. And you can kind of think of these as isolated supernova as well. And yeah, if I did the back of the envelope calculation for the number of stars you expect in isolation, and it's very comparable, like the number of 1As and core collapse supernova that you have in this. So one of the things that I've been meaning to do is to rerun these simulations, including basically a better model for including also type 1A supernova and see what happens. And I kind of expect that the effect will be significantly smaller.
Did you try like high gas fraction in this galaxy? I know there are a few runs with the because then it will be like more extreme regime, right?
So this is a VLM-like galaxy.
Yeah, I mean the Milky Way, like the Milky Way size, but more like in starburst regime, like 40%.
I haven't done that, no, but I could do that for sure.
Thank you.
It's the problem is that they are expensive. So, but I can try. I'll start it and run it in the background for a couple of years.
Yeah, wonderful. So since you have realistic population of black holes, have you thought of having population analysis for LIGO sources, like stellar mass LIGOs, like, black holes and so on?
So I've been thinking of testing it. I have never done it, but like there is a distribution of black holes in the simulation, so it should be fairly easy to look into.
Yeah.
There is some model improvements I would like to do first. For example, I don't give stars or black holes any kicks during supernova, but that would be something that's very simple to do.
Do you have dynamical friction by any chance?
No,
I see.
just
Would that be hard to implement that? Because it's really like that. It actually gives you. I mean, I think
Yeah,
for a
yeah.
realistic population synthesis, you may want to know how they get segregated to the
Yeah.
center.
No, I don't have that. Not at the resolution that we have here.
Okay.
I mean, I guess you can implement a model for it. I've also
Romulus
been-
is cosmological simulation. I think yours is much better. Okay, they're not here. I mean, in terms of resolution and mass and so on, but they have that. We don't have it in TNG, for instance.
Okay.
There's like a mass centering for supermassive black holes, so that would be lovely if you could do it. And a
Yeah.
follow-up is that, is there any chance that these simulations, I'm not saying public, but that will be shareable with others if they
Sure.
have questions? Okay, great.
Yeah, sure.
We should discuss.
One more thing that I've been thinking of implementing is actually binary stars. Basically flagging some stars as binaries. I think that would also be very interesting for example, LIGO sources. You can follow using some simple model for binary evolution would be very cool. And it's possible. Like the stars are there. You just need to flag them and put in the right subgrid models. Thank you.
I was going to actually also ask about binary stars. So I'm curious, like, do you know, like, how and, like, what kind of timeline you would have if you were to pursue that?
I mean, we do think a lot about binaries in this Torch project. So I'm working quite a lot with Claude Coultier, who's implemented binary population into Torch. Now here the evolution is actually traced properly with an n-body integrator, but you can make some simple analytical arguments for how they should evolve. And then you can just flag stars based on some probability function to get binaries in. I think it's doable. I have a lot of projects on the back burner, but yeah, binaries is for sure something that I'm interested in.
Cool. I was also curious about if you have any interest or plans in including POP3 stars in any of the Inferno Edge stuff, or like your thoughts on like the effect or lack of effect of including those.
That would be great, actually. So right now we don't have a POP3 model in the simulations. For early chemical enrichment, where I guess POP3 stars would be most important, we just apply a metallicity floor. So I guess that's our POP3 model, which is not realistic at all. But it shouldn't be too hard to include a POP3 model.
Yeah, if you're already doing individual stars and
Yeah.
feedback tracing, yeah.
Yeah, you just have to, like, I guess you would do something like you're doing in EOS, just below some metallicity, you just use a different IMF
Yeah.
And different stellar evolution models.
Cool. Yeah, that would be interesting to see and compare as well. Are there
I'll
any?
get you involved if you want.
I
You
would
want to implement it.
Oh no! I'm also getting involved in too many things now. But are there any other questions?
I was not sure how to formulate this question, but is there like any more insights that you can learn from this type of simulation about global cluster formation and survival?
I'm trying, yeah. So in edge simulations, we're seeing globular clusters popping up. I don't know if I have it in this. So actually, I wanted to discuss it tomorrow at the
You're coming the Hernquist meeting.
Yeah.
Yeah.
But I can give you a teaser. So when I go into the edge, or these star-by-star edge simulations, we actually see a population of objects that sit here in terms of half-light radius and V-bang magnitude. Keep in mind the resolution limit is right here, right? So, and this is also no collisional dynamics. So a lot of things need to happen, I think, before we can very confidently talk about globular clusters. But the fact that we have something here shows us that we're reaching that point, right? We're getting objects that form in ways where you have very, very high stellar surface densities. And then you get into all this business with like what are interesting chemical chemical features that you find in these, and how do they form, and do you get different population, etc. So this is definitely something that we're thinking about. Keep an eye out for a paper by Ethan Taylor. I guess you probably talked to him or already, or because he's doing the first work on really trying to nail down globular cluster formation in these models.
What was his term for like not dwarf galaxy, but not globular cluster?
He has a new type of
like has a new
galaxy,
name. Yeah.
like that he calls globular cluster like dwarf,
Okay.
where you basically have a galaxy that forms in one starburst, so you get the halo just on limit. So I'm excited.
Yeah. All right. Well, that is perfect timing. Thanks, everyone, and thanks for a fantastic talk.
Thank you.
Yeah, in fact, that was really great because, we normally cannot ask that many questions. So, I'm actually very, very excited if we could collaborate on, my name is Razia Emami. So, actually, if you look me up, I recently have a basically paper about the basically like drivers of the mergers, like unraveling the merger history using the H3 survey data. So, if you just look for like Emami, EMA.